Welcome back. Last class we introduced the last of our series convergence tests, the ratio test, and we practiced it a few times. We're going to try one or two other questions, and then we're going to move on to the next topic of the course. So to refresh your memory, the ratio test applies to a series, the sum of an, and we basically look at the ratio of successive coefficients, an plus 1 over an in absolute value, and we formulate that limit, and if it reaches some limit L, and if L is less than 1, we say that that series converges absolutely. If you end up with an L bigger than 1, the series will diverge. And if L equals 1 dead on, then you essentially get no information out of the ratio test. And at that point, you should consider an alternate test. So let's try it on another example. I mentioned last time that the real wheelhouse of the ratio test is power functions, like 2 to the n, 5 to the n, whatever. And also factorials. Factorials grow very, very quickly, and we saw last class that they, in fact, dominate power functions as you go off to infinity. So we're going to do a little example where we actually pit a couple of different factorial terms against one another, in a sense. So I've got n equals 1 to infinity, and we've got n factorial times n factorial on top, and on the bottom we have 2n factorial. And we have our usual question, does this converge or diverge? All right, so let's get into this. The solution always starts with the ratio test by formulating the limit as n goes to infinity of an plus 1 over an. And in order to do this now, I take the series expression that's given to me and I replace all the n's with an n plus 1. So I get n plus 1 factorial, n plus 1 factorial. And then importantly, we went over this last class, make sure you use your brackets, 2n plus 1 factorial right there. That's important because that actually, when you expand it, becomes 2n plus 2 factorial, not just 2n plus 1 factorial. All right, we divide that by an, and we've seen this a few times. Now that we have an expression in fractional form, it's easier to multiply by the reciprocal. So we put a 2n factorial up here, and we have an n factorial twice on the bottom. All right, so I've multiplied by the reciprocal, and now I'm just going to stack like terms. So I have, they're all positive again, so we don't need the absolute values. But I have an n plus 1 factorial over n factorial, and I have that again. I'm going to write that again. And then I have a 2n factorial over 2n plus 2 factorial. I forgot my limit notation, so let's chuck that in. Limit n to infinity. Okay. So now I write the first term as n plus 1 times n factorial. That's divided by n factorial. Do the same thing with the second term. That is, take the larger of the two factorials you're comparing and start pulling terms off till you get the smaller one, and then leave the rest as in factorial form. And then right here I have 2n factorial, the smaller of the two, and then the 2n plus 2 factorial. Start pulling off terms, 2n plus 1, until you get to the other factorial that's in the other portion. Now that's gone and that's gone, as are these two, as are these two, and I'm left with n plus 1 over 2n plus 2, 2n plus 1. Okay, and if I work this out, I get on the top n squared plus 2n plus 1, and on the bottom I get a 4n squared plus 6n plus 2. Now as n goes to infinity, we have two polynomials in n, and many ways to approach this, but the simplest is probably to realize that the top and bottom have the same degree, and so we can simply take the ratio of the leading coefficients. That's the 1 in front of the n squared right here, and then the 4 in front of the n squared on the bottom. So any way you cut it, the ratio of those coefficients is 1 over 4, which is my L value. It's this limit expression that I've formulated here. All right, so since L is less than 1, it's 1/4, then by the ratio test, this series, which I can write as such, converges. So we see that a 2n factorial dominates a product of n factorials, as it turns out. You can think about that a little bit, and it probably makes sense as to why that might be the case if you throw in a couple of n values and see what it's doing. All right, so the ratio test seems to be a pretty nice tool, and it's really nice because you don't have to come up with anything in order to reason out your argument, unlike, say, the comparison test or the limit comparison test, where you have to kind of figure out your bn, or you have to figure out some comparison to make to a simpler function and so on. So you have to kind of be a bit creative in those tests. Here, you just, if you decide to use the ratio test, you simply compute something and make a conclusion based on the L value that you compute. So since this is all working quite well, let's try the ratio test on a series that maybe doesn't quite look like some of the others we've been using it for. I'm going to go n minus 4 over n cubed plus n minus 1. Okay, so I'm converge or diverge, my usual question. And I'm going to try the ratio test just to see if we can get anywhere with it. I'm noting, I look up there, I don't see any exponential functions. I don't see factorials, so I'm not seeing the usual things that might key me into thinking the ratio test would work. Nevertheless, it seems to be pretty elegant, so let's give it a go. Always starts with the same expression, this ratio of an plus 1 over an in absolute value. An plus 1 means take the series expression and take all the n's and make them n plus 1. Plus 1 cubed plus n plus 1 minus 1. All right, there's the first one. Multiply by the reciprocal to divide by an. So that gives me an n cubed plus n minus 1 all over n minus 4. All right, so I look at this expression and it's a little bit now, what would I say, probably annoying to expand out the n plus 1 cubed and then group all those together and then further multiply out what will end up being 6 different terms on top and bottom. You can do it, but if you would do it, you'd end up with limit as n goes to infinity. The top power and bottom power are both going to end up being quartic, degree 4. And so if we work this out, I'm not going to write all the terms, but the first term is going to be an n to the 4th plus and then some other stuff. And on the bottom term also it's going to be n to the 4th plus some other stuff, lower power stuff. Again, if we look at the ratio of leading coefficients here, that's all we really need to formulate this limit, and we would get 1. All right, and so in this case, L equals 1, and the ratio test gives no conclusion. Meaning we wasted our time, effectively. So if you looked at this original series up here, it turns out that it's not set up for the ratio test. The ratio test gives you 1, and it also gives you a limit expression that's a little bit annoying, let's say. A far better test to use in this case would have been the limit comparison test, where I would use my bn equal to 1 over n squared, which is kind of the limiting behavior of the leading power of top and bottom, n over n cubed or 1 over n squared if you reduce that. That would end up converging when you worked it out, but what I'm trying to get across is that every one of these now 7 different testing approaches has their own little style and type of an terms that they work really well with. And they don't always work in other contexts. Sometimes they do, sometimes they don't. But here the ratio test doesn't give us anything. So sometimes the ratio test will lead you to a limit expression that is very difficult to work with, or it'll just give you 1. And in both of those cases, you might try a different test instead. All right, so we have a little bit more practice under our belt. And we're going to move on now and we're going to go back again to one of the very first series that we talked about in this class, geometric series. All right, and so we would write this as the sum from n equals 1 to infinity, ar to the n minus 1. I'm simply going to rewrite this. I'm going to rewrite as the sum n equals 1 to infinity, ax to the n minus 1 instead of ar to the n minus 1. And I'm just going to rewrite it again. I'm going to do one other little modification to this. I'm going to go n equals 0 to infinity, ax to the n. Okay, which is the exact same thing. These two series are the exact same thing. I'm just changing the index. Instead of starting at 1 and then writing the n term as n minus 1, I started at 0 and just have x to the n. So they give you the exact same expression. If you plug in n equals 0, you get a, and then you get ax, and then ax squared, and so on. Now, I changed the r to an x, which doesn't change the mathematical nature of the geometric series. But the x we often use as a variable, and so we're going to keep that in mind moving forward. I might say before a series, like some sort of sum of an, we could think of this as a kind of a placeholder for a value. If it converged, the series would converge to a number, maybe 2, maybe 3.5, whatever it is. Or it diverges and maybe goes off to infinity or never settles down upon a value. But if it did converge, it would give you a value. Now that I've changed the r to an x, I want to start the idea that instead of fixing the elements of a series such that the series will converge to a number or not, we more think of the component of the series, the x, as a variable. So we're just going to think of x as a variable. All right, and by that I mean we can plug a value of x into the series, and then the series for that value of x will return a value to us, much like a function does. Okay. So then this n equals 0 to infinity ax to the n thing is a function. X goes in, the series gives you back a value. Now, it doesn't give you back a good value for all of the possible x values you can put in. If you put in x equals 2, for instance, it would give you back infinity. But there is a range of values of x where this will give you a non-infinite value. And specifically, we remember that it's still just a geometric series. We know where it converges. It converges anytime I make x there equal to a value between minus 1 and 1. Before we said r was between minus 1 and 1, or less than 1 in absolute value. Now we're just changing it to an x, and we think about x ranging through some values. It's kind of like the domain now of the function that's given by the series ax to the n. All right, I'm just going to slightly change the series. Now consider, I'm going to, just as an example, do from 0 to infinity 2 x minus 1 to the n. And I'm going to ask this. What x values does this series converge for? I did the same thing. If I thought of x as a variable and I'm looking at the window of values of that variable that will lead to convergence of this series. All right. Now the a in this case is 2. That's not really doing much, but it really is this x minus 1 term in the series that's going to determine it. Now if that was just x to the n, it would be the same as my previous question, ax to the n, and I'd say, okay, it's from minus 1 to 1. But it's now x minus 1. So it really is that x minus 1 term that must be between 1 and minus 1. And now if I wanted to find the range of x, I can just solve this inequality for x. And I do that by adding 1 on to every value. All right, so now I look at this related series and notice that this series will converge so long as x is between 0 and 2. And again, I think of this kind of like a function, and now the function has a bit of a domain. And inside that domain, I expect that series will return a value for me. Now, this concept is really, really important because often we will use series as representations of functions. And when we do that, we would like to remove the function and replace it with a series. Or maybe if we have an equation that doesn't have a function that solves it, we want to replace that solution with a series. But we want that series to converge for us. That's when it converges, it's giving us something useful. So we are very concerned about ranges of values we put into a series that will give us values out that make sense or are useful to us. And these kinds of observations are leading us into a new kind of a general series that we're going to talk about in this course. They're called power series. So we're going to start off power series with a little quick definition. A power series is simply a sum of constant coefficients times successive powers of x minus a. So the variable x, there's a constant a, and so it might look like something like some c0, some coefficient, and then a c1 x minus a, and a c2 x minus a squared, and it keeps going up like this. Okay? And of course I can write this in summation notation, n equals 0 to infinity. Some Cn, this constant coefficient that does change potentially with every n value. Okay, so it can change all the way through. It's not like the fixed value of a in my geometric series we've seen before. And then there are these successive powers of x minus a. All right, so these Cn's, we call them coefficients, as above. These are real numbers that can vary with n. So they generally depend on n in some way. It could be, 4 over n. It could be 2 to the n over n factorial. It can be a whole bunch of things. The a is some constant value, a real number, 3, minus 4, whatever it might be. And the x here is our variable. So we can put an x value into the series, and it should, provided it converges for us, spit us out some value. And so we're really interested at this stage in what x's can I put in for a given power series and expect that to converge. So interested in values of x that make this sum n equals 0 to infinity cn x minus a to the n converge. Versus diverging. Now, one observation. What if x equals a? Let's go up to the series. If x equals a, in here, plugging x equal to a just gives me a minus a, which is 0. And that happens for every term, basically, except possibly 0, when n equals 0. We're going to talk about that in a second. But effectively, if we start writing out these terms, let's walk down here. So I'd get, in the first term, C0, 0 minus 0 to the 0, plus C1, 0 minus 0 to the 1, plus C2, 0 minus 0 to the 2, and onward. Now, 0 to any power that's not 0 is always 0, so that's gone and that's gone, as is every other term forward. The only slightly curious thing is this term. This C0 is 0 minus 0 to the 0, which is C0, 0 to the power 0. And so you might wonder, what is that? A 0 to the 0 is defined to be 1. And so you end up with, when you do this, C0. Now C0 is a constant. It's a finite constant. So at x equals a, this series converges to the value C0. So that means every single power series will always converge at the value x equals a. And now the question is, as we move away from x equals a, how large of a window of x values are there that leads you to convergence? And so we have a way of drawing this and denoting this idea. So if we have some a value, definitely the series will converge there to C0. We can step off some value r in either direction, like this. This little r, the distance I can move away from a until I stop converging. So that range of values for which I converge in terms of a distance away from the a is called the radius of convergence. If I look at the whole thing from a minus r to a plus r, I call that I, which is the interval of convergence. So if you have the a value and you have the r value, you can just compute I by going a plus r, a minus r. So they're one and the same. But this r value, this radius, can actually take on a number of values that have a number of different meanings. So r can be 0, a 0 radius of convergence. And what that means is it converges only, everything converges at x equals a, but if r is 0, you can't step off from a without diverging. So let's actually clean that word up. So this converges for only x equal a, the single point. If I move off that, I instantly diverge. It can be infinity, okay, which means the radius is infinitely long, and this means it converges for every x value. Doesn't matter how big x gets or how large negative it gets, the series will still converge. Or it can be a finite value. And what we do is we look for this kind of magic formula, a statement that x minus a is less than r in absolute value, where it converges, and then that implies that if you're outside of that, greater than r, then your series diverges. Okay, or in this number line notation, we have an a definitely converges there. If we have some finite value of r, then all through here, the series converges to a plus r, a minus r, and then outside of that, on both sides, the series diverges. Okay, and this is the x number line here. Now, for a given question, how do we find r, whether that might be 0, infinity, or some finite value? All right, so there's a really nice thing that happens. We want to go out and find this value r. And we don't have to build any new machinery whatsoever to find this value of r. We simply use the ratio test, that test we just finished off studying for convergence of series. We also use it to study power series and look at the radius of convergence. So we're going to see how this works in an example. I'm going to give you just some example of a power series, and we're going to try to construct the radius and then the interval of convergence for the series. And so in this section, the only series test of all of the ones we did that we need to carry forward in terms of our computations here is the ratio test. All the others are for the more general form, the sum of an type series that we've been looking at the last while. All right, so here's the example. Get the radius and interval of convergence for the series, the power series, n equals 0 to infinity. And the terms are going to be 2 to the n over n. Those are the coefficients. And then the form is x minus some constant, it'll be minus 2 in this case, to the power n. And so what we want to know is when we look at this expression, what values of x can I plug in here that will lead to this entire expression being a convergent series versus being a divergent series? All right, just so that we have our notation clear, these terms here are the CNs. Okay, this bit here. This thing here is my A value, and that's really all I need. Solution: use the ratio test. That's all you need for the radius and interval of convergence. If you see that question, go right to the ratio test. Limit is n to infinity of an plus 1 over an in absolute values. Now let's plug these terms in. An plus 1, 2 to the n plus 1 over n plus 1. X minus 2 to the n plus 1. And now for the first time in all of my examples, I'm going to really want to focus on those absolute values because it does matter. Now x minus 2 can be positive or negative depending on the value of x. So we do want to carry those absolute values through now. We're going to multiply by the reciprocal, also an absolute value. So that's going to be an n over 2 to the n, x minus 2 to the n. Now what I'm going to do next is take the terms that are similar in nature, that just differ by the n plus 1, and I want to stack them upon one another. And what I mean by that is kind of take the 2 to the n plus 1, this term, and I want to take the 2 to the n here, and I want to pair those together because I expect some cancellation to happen. That just reduces down to 2, for instance. I have an x minus 2 to the n plus 1. And, oh, a little mistake here. This x minus 2 is on the bottom here. Right there. Sorry about that. I forgot to reciprocate that term as well. All right. So down here, I have an x minus 2 to the n plus 1. X minus 2 to the n. That's an absolute value. You can see I've pulled the absolute value off of the 2 to the n plus 1 and 2 to the n terms. They're positive, so it doesn't matter. Same thing with the n and the n plus 1. Those are positive terms, so I don't need the absolute values. Now, I can move that absolute value. Well, there's a 2 there, but the absolute value, the terms in there reduce down to an x minus 2 just to the power n plus 1 minus n, or to the power 1. So that whole thing becomes x minus 2 in absolute value. And then I have the n over n plus 1. And this term here is the only thing that involves n going to infinity. So if that's the only thing that involves n going to infinity, the other stuff can come outside of my limit. So it equals 2 x minus 2 in absolute value, and then the limit as n goes to infinity of n over n plus 1. And again here, this limit, you can either divide top and bottom by n to find it, or you can look at that as the ratio of leading coefficients of a polynomial of degree 1 over a polynomial of degree 1. But that limit equals 1. So you get 2x minus 2 times 1. And now here's the big thing. The ratio test says formulate this limit. Call that limit L, and if L is less than 1, then your series will converge. We've formulated that limit, and we've got an expression. Now the expression now involves x. It didn't before, but now we've got a power series, so it involves an x. And so the next thing I do is I say, all right, that has to be less than 1. Okay? So this thing is like my L that I've found, and I am forcing that to be less than 1. Okay, I don't know if it is or not. It depends on x in this case. So what this is, it's the condition that the ratio test needs to satisfy to obtain convergence. So instead of before we just found our L, maybe it's 2, maybe it's a quarter, whatever, that number just basically says, yeah, you converge, no, you diverge, whatever it might be. Now we are imposing the condition for convergence. And when we do that, then I get this statement, 2, I'll just rewrite it, less than 1. Now, we had this holy grail format. We would say we would get R by getting an expression for convergence where x minus a is less than R. Over here, I'm pretty close to that. I have 2, and then x minus a in absolute value, less than a number. So it's almost set up this way. It's just that that 2 is in the way. So I'm going to rewrite this as x minus 2 less than 1/2. And now I can use this format, the x minus a less than R, and I have it. Okay. If I look at this, the a value is 2 here, not minus 2, but it's positive 2 because it's x minus a. And the R value is given right here. The R is 1/2. As soon as I get this format, I knew what a was from the very beginning, by the way. The a is just this value 2, and it lives on through this calculation down to here. So it's still a equals 2, but this also gives me my R equals 1/2. So I've got my radius of convergence R, and my I is simply a minus R, a plus R, which in this case is 2 minus 1/2, 2 plus 1/2, which is equal to 3 over 2 to 5 over 2. All right, so that's how we compute a radius and interval of convergence.